So for this example, we're going to look at this equation, and they're asking us to find vertex, axis of symmetry, domain, range, and they want us to graph. And the good thing, they do tell us that we do have a parabola. It's a good heads up, and we kind of know what section we're in. But I kind of want to point out, even though we are in the parabola section, completing the square is the #1 way to determine what type of conic section you have if it's not written in its nice standard form. So this is where I'm going to always go to if ever I'm faced with a type of problem where they want us to graph an equation that we're not quite familiar with seeing. So I like to point out, even though they tell us it's a parabola, take a look at all the terms one more time, and then notice that it's the y term that's being squared. So again, that's going to give us those horizontal parabolas. And you can even tell a little bit more from this equation. The coefficient of the squared term is positive. So that even justifies why we'll be taking a parabola that's going to be opening up towards the right. So it's really cool if you can look at the equation and predict what the picture will be. That way, when you do the work, you're going to actually have a nice verification that you're actually correct. So like I said, because they're not asking for the focus or directrix, we can put the parabola in standard form. And so just if you remember, the standard form of a parabola. So what do we have? Normally, we were used to seeing y equals a times x minus h squared plus k. But remember, we have the squared term. So this will be, we're solved for x. So we should have a times y squared. And remember, when you're associating things with the y terms, it's going to be y minus k. And this time we have the plus h on the outside. So this again is our horizontal parabola. And I'll erase the other one just in case. I always like to compare it to the one I'm more confident with, and then I can kind of see the differences as I go. So our goal is to get our original equation into this nice vertex form, our standard form. So what we'll do, I'm going to rewrite it so you see. If I am completing the square, there's a couple ways I can take this, but you may just consider moving the 8 to the other side. You don't necessarily have to. I just like to get it out of my way. So I will do that. I'll subtract 8 from both sides. That way I don't forget anything special. But my goal is to see that I'm actually completing the square on the y squares. And so what we're going to need is a formula. That's where we take half of the linear term and we square it. So I'll do that in green to make it stand out. So the linear term is 6y, so we're saying half of 6. We're squaring that. Half of 6 is 3. When you square 3, you get 9. So in order to make this binomial a perfect squared trinomial, we have to add 9 to this side. But if we add 9 to the right-hand side, we also have to add 9 to the left-hand side. So I'm going to squeeze that in there. Now that we have our perfect square trinomial, we can go straight into the factorization. We do know that when it factors, it will be the same term repeated twice, and it is y plus 3 squared. If you want to simplify the left-hand side, x minus 8 plus 9, so it was an x plus 1. So we're almost set. All we have to do now is just move that 1 over. If you want to make it look like the standard form, you could also probably recognize it in the forms that we've been dealing with in this section, but might as well. If we're focused on standard form, we can go back. So that would leave us with, if we subtract 1 from both sides, we are going to be left with x equals y plus 3 squared minus 1. So that is our nice standard form. From that particular equation, what we can do for ourselves is name who the vertex is. That's the first thing they asked us for anyways, so I'll write that off to the side. So remember, the vertex is the h comma k, but the h is -1, exactly what we see. And then the k is -3. So we could plot that if we're here, -1, -3, got our vertex. We know that it's going to be opening up to the right, so it's kind of a heads up from there. The other thing they're asking us is, what is the axis of symmetry? So I'm going to make a more accurate graph in a second, but I want you to see when you open up your parabola to the right, your axis of symmetry is the line that goes straight through the vertex. So if I can draw it, our axis of symmetry would be a horizontal line in a horizontal parabola. So axis of symmetry. And if you really look at it, you notice that horizontal lines always have the equation y equals a constant. And so all you have to do is figure out where it hits the y-axis, which is at -3. So see how it's related. The y value of the vertex for the horizontal parabola. Now they want us to talk about domain and range. We could probably do this from this quick little sketch if you'd like. But I would like to find 2 other points on the parabola that will make me determine the width. It kind of just makes me feel better before I find the domain and the range. So remember what our equation is. I'll write it out off to the right. So I have x equals y plus 3 squared minus 1. And what I might do, I might pick the y values that I want to see. Perhaps you want to figure out what's happening at y equals 0. We can use symmetry to help us out there. So let me see if I can find, yeah, there we go, purple. So I'm just plotting points. If you'd like to convert it back to the focus and directrix form that we were dealing with, that might be fun too, to figure out what the latus rectum is. But it's solved for x, so I'm just plugging in a few values of y and going to use symmetry to help my graph that. So if I have y equals 0, I have x equals 0 plus 3. I should color code that for you. So 0 plus 3 squared minus 1. So what does that give me? 3 squared minus 1, which is 9 minus 1, are 8. So remember, when you make the ordered pair from this, remember that you're always putting the x value first, which is 8, and the y value second. So when y equals 0, x is equal to 8. Okay, so if you want to plot that, 8 comma 0, 1, 2, 3, 4, 5, 6, 7, 8. Now, if you'd like, you can use the axis of symmetry. Notice that it's 3 units away from the axis of symmetry, so you can go the same units away vertically. And by symmetry, we can plot another point on the parabola. So that makes it nice. If you want to be a little more accurate, sometimes I'm more interested in finding points that are closer to the vertex. So maybe a y value like y equals -2 could help me just kind of have more idea of what the width would be. Y equals -1 could also be nice. So I'll just take a little more time. Y equals, let's just say, let's do -1. It's more friendlier, but feel free, pick more if you need to. So that's going to leave me with x equals -1 plus 3 squared minus 1. So we do the math. We should have 2 squared minus 1, which is 4 minus 1, which is 3. So when we make our ordered pair, remember it's the x value that goes first, the y value that goes second. So 3 comma negative 1. So if we have 3 comma negative 1, we are located here. So that's going to give us a pretty good accuracy. Also note with the axis of symmetry, if you're 2 units away, you can go the other way to get another point. And if you feel the need to, if you want to draw another point, if you want more accuracy, feel free. But right now, I think we're good enough. We just know that the parabola, it's a U shape and it's opening up towards the right-hand side. It's a little crooked. Please forgive my crayon on that one, but now we have the idea. So that's a nice graph. I know we get excited when we're done graphing, but double check the directions one more time. Did we find the vertex? Check. Did we find the axis of symmetry? Yes, we stated that. Did we find the domain or range? No, we still need to do that, but we did graph the parabola. So like I said, just by looking at the graph, we can start naming what is our domain and range, and I'll label it a little nicer for you. So a little bit of practice coming back from our past. My domain would be all the possible x values for my parabola. So if you notice, whenever we're dealing with domain, we always start on the far left of the x-axis. And anything that's happening at x equals -10 is probably happening at x equals -infinity. So notice there's no graph above or below. So we keep traveling closer to the origin until we find a graph, a corresponding y value. And right here at x equals -1, that is the starting point of our graph. Now notice once you go beyond a -1, a little more to the right, you're always going to have a graph for the most part below, and then when you get a little closer, it ends up being above. So when we're at the far edge, the far right of the x-axis, notice that we always have a graph above or below us. So our domain would actually have an endpoint at infinity. So we go from -1 to infinity, and -1 is included. Now, if we're going to approach this the same way with the range, the next thing you do for yourself is just kind of picture yourself on the y-axis. So if I can, I'm running out of colors. I'll go along with erasing my red, just so that we can demonstrate that together. But not my entire parabola. There we go. So if we're starting off at the far, I should say the very bottom of the y-axis, y equals -10, you just look to the right and left of you and just try to understand, do you have a corresponding x value? So notice we can't quite see it, but we do know how parabolas work. Even if they look like they are leveling off, we do know they get wider and wider and wider and lower and lower and lower. So my range is actually going to be at -infinity. And as you travel up the y-axis, you're always having a picture to the left or to the right of you. And even when you're a little bit taller, you can go way up here, the very top of the y-axis, at least for the coordinate system. And notice, even though the parabola looks rather narrow, the behavior of the parabola gets wider and wider and wider and taller and taller and taller. I'm going to erase that for now. So we can tell ourselves that the range is -infinity to +infinity. So it's a nice little practice. It kind of brings us full circle to what we were dealing with in, I believe it's section 1.3, looking at the graph, finding the domain and range. But there's a lot of algebra involved in this problem, and a lot of the algebra is valuable to us later for our future math courses. So kind of get into the habit of looking at a conic section, understanding that you can use completing the square to put it in a nicer form to make it nicer for you to graph. And also the concept of reading the graph and finding what the domain and range is from it. So I hope this helps. I will see you in the next example.